Hi, in this video I'm going to guide you step by step on how to use the i4i Brittle Fracture Screening Tool for API 579 Part 3. The link to the tool is in the video description, and this video is meant to be used together with the tool. API 579 Part 3 exists to help prevent one of the most dangerous failure modes in our industry, brittle fracture. Brittle fracture can happen suddenly when steel is cold enough that toughness drops, and if a crack exists or can initiate, the fracture can run fast with little warning. Part 3 helps you screen whether your situation needs a deeper fitness for service evaluation so you can establish safe operating limits and avoid pressurizing equipment when conditions are unsafe. Before we start, I want to explain two key terms in a simple way. CET means the coldest metal temperature your equipment can realistically see in any credible scenario. That includes startup, shutdown, standby, upsets, unexpected depressuring, and even unusual conditions that do not happen every day. CET is not just the ambient temperature. It is the metal temperature at the time the equipment could still be under pressure or other significant loads. MAT means the minimum allowable metal temperature you should permit for safe operation. If your credible CET can drop below your MAT, then you're in a region where brittle fracture risk becomes a real concern, and you should not rely on assumptions. Now here is how to use the i4i screening tool. You will answer every question from 1 through 30 by selecting yes, no, or NA. Use NA only when the question truly does not apply to your equipment. For example, if a question is clearly about storage tanks and you are screening piping, then NA is appropriate. But do not use NA just because you are unsure. If you are unsure, treat that as a sign you need to gather information before you can confidently screen the equipment. After you answer all questions, click the button that says Check if FFS is needed. The tool will give you a result. If the tool indicates that a fitness for service evaluation is likely needed, that does not mean you failed. It means the screening found credible conditions where you should establish a defendable basis using the proper assessment steps rather than guessing. Now let's go question by question with detailed refinery scenarios so the logic becomes very clear. Question 1 asks if brittle fracture is a potential integrity concern based on metal temperature exposure and operating conditions. A realistic refinery scenario is a cold side exchanger channel, where, during winter startup, cold feed is introduced before the exchanger metal warms up. The metal temperature can temporarily drop far below what you see during steady operation. Another scenario is a light ends receiver that becomes cold after depressuring. Even if the air temperature is not extreme, rapid pressure drop can chill the metal. If you have any credible scenario where the metal can get cold enough that toughness may be reduced, select yes. Question 2 asks if you need to establish or confirm a pressure temperature operating basis. This is common when operations wants a written and defensible envelope before restart. For example, management may say, before we approve winter operation, we need to know the minimum metal temperature allowed at normal operating pressure and during startup pressure ramps. If your facility is asking for a documented pressure temperature basis, select yes. Question 3 asks if you are changing operating conditions or re-rating in a way that requires reconfirming limits. A realistic case is an MOC, management of change, where process changes lower metal temperature at the same pressure, such as colder feed, different control strategy, or changed heat integration. Another case is when you increase pressure, but winter low temperature exposure is still possible. If you are changing the operating window, select yes because your old pressure temperature basis may no longer be valid. Question 4 asks if your decision basis is tied to CET and/or MAT and you need to establish or confirm acceptability by comparing controlling CET to MAT or to the pressure temperature basis. This question is basically asking, are you making a go or no-go decision that depends on low temperature acceptability? A refinery example is when a unit wants to start up at a certain cold temperature, and you need to justify whether pressurization is acceptable. If your decision depends on temperature acceptability, select yes. Question 5 asks if you have the required level 1 basis inputs available. Here is a common real refinery situation. You have an older vessel from the 1970s. The drawings may be incomplete, the nameplate is damaged, thickness information is inconsistent, or repair history is unclear. If you cannot confirm the basic inputs like year of fabrication, nominal thickness, design minimum temperature information, or other required basis inputs, select no. Missing key inputs means screening cannot be defended and you will likely need more data or a more rigorous route. Question 6 asks whether original hydrotest records are part of your brittle fracture basis. This applies when your argument depends on hydrotest history. For example, someone says it was hydrotested at a high pressure long ago, so it must be safe. If the hydrotest is part of your logic, you must verify the hydrotest pressure and the temperature conditions that existed during the test. If hydrotest records are being used for your decision basis, select yes. Question 7a asks if Sharpie impact data is available. Sharpie impact data is direct evidence of toughness. A refinery example is finding MTRs that include impact results for the base plate or welding records showing impact tests for weld procedure qualifications that truly apply to your component. If you have relevant Sharpie data, select yes. Question 7b asks, if Sharpie data is not available, does your API 579 Part 3 path need to address missing impact data? This is extremely common for older equipment. When you do not have impact data, you must recognize that your evaluation will rely on conservative screening paths and assumptions appropriate for missing toughness documentation. If you do not have Sharpie data, select yes here to acknowledge that missing impact data must be handled properly and not ignored. Question 8 asks if your current concern is primarily a crack-like flaw acceptability case rather than temperature-based screening. This is a very important fork. A refinery example is when PAUT finds a planar indication at a nozzle-to-shell weld, or a weld shows lack of fusion type indications. In that case, the main question becomes whether that flaw is acceptable, and that is not purely a Part 3 temperature screening problem. If your issue is driven by a crack-like flaw, select yes. Question 9 asks if the pressure boundary material is outside the intended screening scope. This question is about applicability. If your equipment material is uncertain or not within the expected carbon or low alloy steel pathway intended for this screening approach, you should select yes, because you must verify the correct assessment route before relying on screening results. Question 10 asks if the equipment type is covered, such as pressure vessels, piping, or certain above-ground tanks. If you are screening a pressure vessel drum, a piping circuit, or an atmospheric storage tank shell course, select yes. If you are trying to apply this tool to something outside those equipment types, select no. The question 11 asks if the equipment is included in an in-service inspection and maintenance program. A realistic refinery scenario is the difference between equipment on an active API-style inspection plan with known history and intervals versus an orphan piece of equipment with unclear inspection ownership. Screening decisions are much stronger when the equipment is part of a disciplined inspection program. If the equipment is not in that type of program, select no. The question 12 asks if environmental cracking is credible or if there is a credible service condition that may reduce toughness. A refinery scenario is service where you have reasons to believe toughness could be reduced or where certain exposures make brittle fracture resistance more uncertain. Another scenario is where long-term service conditions may have affected toughness. If toughness, degradation, or environment-related concerns are credible, select yes. Question 13 asks if metal loss exists. Have you qualified the metal loss and also performed supplemental inspection to confirm no crack-like flaws exist? Here is a detailed refinery scenario. Suppose UT mapping shows thinning at a nozzle neck or a shell region. You qualified thickness, but the highest risk locations are often near welds and geometric stress razors where cracking could exist. If you have not performed appropriate supplemental crack detection inspection in the areas that matter, you cannot safely assume there are no crack-like flaws. If that supplemental inspection has not been done, select no. The question 14 asks if you need an explicit load versus temperature envelope, implying a level 2 approach. A refinery scenario is when operations wants a practical operating curve. They want to know allowable temperature for different pressure levels during startup ramping. If the decision is not just one number but a full envelope, select yes. Question 15 asks if you are relying on or planning a hydrotest or low temperature pressurization event as part of qualifying continued service. A common scenario is a turnaround hydrotest planned during cold weather where the vessel may be cold in the morning and then pressurized. If you plan any pressurization at low temperature, including hydrotesting, select yes. Question 16 asks if there is potential for shock chilling, meaning rapid metal temperature drop when much colder liquid or two-phase fluid contacts the metal. A realistic refinery scenario is a relief event or upset where flashing occurs and cold two-phase fluid suddenly contacts the inside surface of piping or a vessel region, rapidly chilling it. Another scenario is a cold stream introduced into a hot system, causing a rapid quench. If shock chilling is credible, select yes, because that indicates higher rigor evaluation is typically needed. Question 17 asks if the component is SA212 grade B or you suspect it. In real refinery conditions, this can come up with older equipment where documentation is incomplete. If you suspect older materials that require extra caution and more thorough crack-focused inspection, select yes. Question 18 asks if inspections detected fabrication or material flaws that are non-growing but could affect operating limits. A refinery example is an original fabrication indication that was acceptable for decades at warmer conditions. Now, the unit wants to run colder or change pressure conditions, making that old indication more significant. If known non-growing flaws exist and operating conditions are changing, select yes. Question 19 asks if you have or can defensively establish design temperature and the controlling CET. A refinery scenario is outdoor equipment where the real minimum metal temperature depends on startup procedures, low flow conditions, wind effects, depressurization cooling, and upset cases. If you cannot defend what the controlling CET is, select no. The question 20 applies to storage tanks and asks if you have tank-specific level 1 data like product-specific gravity, design liquid height, and hydrotest temperature when applicable. A detailed scenario is an API 650 tank in a tank farm, where you need to understand shell stress driven by liquid head at low temperature. If you do not have specific gravity or design liquid height or the relevant hydrotest information, select no. If you are not screening a tank, select NA. Question 21 asks if a hazards review identified credible minimum metal temperatures lower than previously assumed. A refinery scenario is when a PHA or operating review identifies a new credible cold start or depressuring case that drops metal temperature below the basis you historically used. If a formal review revealed lower credible temperatures, select yes. Question 22 asks if the equipment was built to an older code edition where brittle fracture prevention rules may not match modern practice or the basis is uncertain. A realistic scenario is older equipment with limited documentation on impact requirements or low temperature design rules. If your brittle fracture basis is uncertain due to age and incomplete code documentation, select yes. Question 23 asks if you need to establish or confirm a minimum hydrotest temperature or hydrotest conditions. This applies when you plan a hydrotest during cool conditions or when you want to rely on a historical hydrotest but cannot confirm the temperature conditions. If you need to establish or confirm the hydrotest temperature basis, select yes. Question 24 asks if repairs or alterations occurred that change PWHT assumptions. A refinery scenario is a vessel originally PWHT'd, but later repairs were performed without PWHT due to schedule and practicality. If PWHT history is mixed or uncertain, and it affects screening assumptions, select yes. Question 25 asks if there is an active or credible cracking mechanism present or suspected. A detailed refinery scenario is a circuit with credible cracking mechanisms where cracks may exist during operation, especially near welds and high-stress areas. In that case, brittle fracture risk cannot be screened as a temperature-only issue. If cracking is credible or suspected and not ruled out, select yes. Question 26 is tankage only and asks whether membrane tensile stress is expected to exceed 8 ksi at the controlling low temperature case considering coincident loads. A realistic tank scenario is a tall tank at high liquid level during cold weather where shell stress is higher and you're combining the worst credible coincident conditions. If you are screening tankage and that stress threshold could be exceeded, select yes. If you are not screening tankage, select NA. Question 27 asks if the lowest one-day mean atmospheric temperature is part of the controlling CET scenario. A detailed refinery scenario is outdoor equipment or tanks that can sit idle overnight, where metal temperature can closely track ambient minimums. If your CET is driven by ambient minimum conditions, select yes. Question 28 asks if you rely on a warmer minimum than the site's lowest one-day mean ambient. Do you have procedures and controls that reliably prevent exposure below that enforced minimum? A good scenario is a unit that has a hard rule. No startup or pressurization below a defined temperature, and it is backed by instrumentation, alarms, and interlocks that prevent operators from accidentally violating that rule. If you do not have strong enforceable controls, select norm question 29 asks if upset or failure scenarios could drive CET lower. A detailed refinery example is utility failure, control valve failure, pump trips, or sudden depressurization that unexpectedly chills the metal below normal assumptions. If credible upset scenarios exist that can lower metal temperature, select yes. Question 30 asks if autorefrigeration due to depressurization, including potential repressurization before warming back up, is credible. This is one of the most important real-world scenarios. Imagine a blowdown event chills the metal rapidly. Then the unit tries to stabilize and repressurize before the metal warms back up. This is a classic brittle fracture risk moment because you can have cold metal and pressure returning. If that scenario is credible in your unit, select yes. Now let's talk about what the final result means. If the tool indicates that an API 579 Part 3 fitness for service evaluation is likely needed, that means your answers suggest there are credible scenarios, missing inputs, or conditions that require a defendable engineering basis rather than assumptions. That is where you gather the right data, define the controlling CET scenario, and establish allowable limits such as MAT or a pressure temperature envelope. If the tool indicates that a formal Part 3 FFS evaluation may not be required, it means you did not trigger those conditions based on your current answers and information. But it does not mean the equipment is safe forever. If operating conditions change, if new upset scenarios are identified, if repairs occur, if new inspection findings appear, or if you plan cold pressurization or hydrotesting, then you should rerun the screening. Let me close with the most important takeaway. This tool helps you avoid the dangerous habit of guessing at low temperature safety. It forces you to think through credible cold scenarios, pressure and load conditions, inspection and flaw considerations, and the quality of your records. Used correctly, it becomes a practical, repeatable gate that tells you when it is time to do the deeper engineering work.